Starting with matrices and determinants. In the first class, I'll introduce matrices. We'll look at various types of matrices, and we'll also have an idea as to what is determinant of a matrix. Now, matrices happen to be an integral part of linear algebra. Traditionally, algebra was the art of solving equations and the system of equations. So, linear algebra is the art of solving linear systems of equations. Let's start with the definition of a matrix. I'll quickly run through the definition because most of this you all have done in the 12th standard. So, we begin with the definition of a matrix. A matrix is nothing but a rectangular array of numbers. It's simply an arrangement of numbers into rows and columns, and we enclose it within square brackets or round brackets. We generally denote a matrix by capital letters A, B, C, etc. The elements in the array are called the entries or elements of the matrix, and the size of a matrix is described by specifying the number of rows and columns in a matrix. So we will say that the size or order of a matrix is m by n if it has m rows and n columns. So when we write the order is m by n, this first number will always stand for the number of rows and the second will indicate the number of columns in the matrix. And for the elements of a matrix, we use the notation Aij. So if my matrix is capital A, I will denote by Aij the element that is in the ith row and jth column of capital A. So Aij will stand for the element in the ith row and jth column of the matrix A. So here the first suffix stands for the row number, second suffix stands for the column number. So for example, if A is the matrix, this matrix has 2 rows and 3 columns. So this is the matrix of order 2 by 3. Notice here that the element A12, that means the element in the first row, second column. The element in the first row and second column is 4. Whereas A21, this is the element in the second row, first column. Second row, first column, the element is -5. So this is the notation that we are going to use for the element of A in the ith row and jth column. In general, if I have a matrix A of order m by n, it's going to look like A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMn. So this being a matrix of order m by n, it has m rows, 10 columns. Everywhere the first suffix tells us the row number and the second suffix gives us the column number. And we can give the same information in a compact form as A equal to square brackets Aij m by n. So this is regarding the notation of a matrix and its elements. Now let's quickly run through the various types of matrices. We start with the zero matrix or the null matrix. If every entry in a matrix is zero, then it will be called the zero matrix or the null matrix. And the zero matrix of order m by n is denoted by capital O m by n. Thus, if I am looking at the zero matrix capital O 3 by 2, this is a matrix with 3 rows and 2 columns, and every entry of this matrix is 0. So it's going to look like, it's a 3 by 2 matrix with 3 rows, 2 columns, and every entry in this matrix is 0. Next, we go to a square matrix. If in a particular matrix the number of rows is equal to the number of columns, and say it has n rows and n columns, then we will say that it is a square matrix of order n. Notice that here I don't need to separately mention what are the number of rows and columns, because if I know that it's a square matrix, then number of rows has to be equal to the number of columns. So if I mention any one number, it is understood that it has so many rows and so many columns. Also in a square matrix, let me make a few changes in this matrix itself. If it's a square matrix and it has n rows, n columns, then the last row is going to look like this: A, n1, A, n2, A, n, n. Look at these elements. For these elements, the first suffix is equal to the second suffix. All such elements, A11, A22, ANN, these are said to be elements on the principal or the main diagonal. So these elements A11, A22, A33 and so on, these are all elements on the main diagonal. All these elements A12, A13, A14, A23, A24 and so on, all these elements are said to be elements above the diagonal, and these elements are said to be elements below the diagonal. I am stressing on the elements above and below the diagonal because I intend to define an upper triangular matrix. So now let's come to the definition of an upper triangular matrix. In an upper triangular matrix, if at all there are any non-zero elements in the matrix, you will find them in this upper triangular region. That means in a square matrix, if at all there are non-zero elements, they will be either on the diagonal or above the main diagonal. That means every element below the main diagonal is necessarily 0. So if at all we are going to find any non-zero elements, they will have to be either on the diagonal or above the diagonal. Again, it's not necessary that these elements have to be non-zeros. We are only saying that if at all the matrix has non-zero elements, they will be in this upper triangular region. Similarly, one can define a lower triangular matrix. In a lower triangular matrix, every element above the main diagonal will be 0, and if at all there are any non-zero elements, they will be on the diagonal or below the diagonal. That means in the lower triangular region. And finally, we will say that a matrix is triangular if it is either an upper triangular matrix or a lower triangular matrix. we come to a diagonal matrix. Once again, we are talking about the square matrix because we can talk about the diagonal elements only in the context of a square matrix. So, a diagonal matrix is one in which, if at all there are non-zero elements, they will be only on the diagonal. And if I take any element below the diagonal or above the diagonal, it has to be necessarily zero. So, if at all this matrix has a non-zero element, you will find it along the diagonal. For example, this is a diagonal matrix because all elements above the diagonal and below the diagonal are zero. Elements on the diagonal can be anything. They could be zero, they could be non-zero. So this is an example of a diagonal matrix. Then we have what is called a scalar matrix. A scalar matrix is a diagonal matrix in which all diagonal entries are the same. So, for example, something like 2 0 0 0 2 0 0 0 2. This is a scalar matrix since first of all it's a diagonal matrix. All elements above the diagonal and below the diagonal are zeros, and all the diagonal elements are the same. Hence, it is a scalar matrix. Notice that the zero matrix of order 2 or any other order, so long as it's a square matrix, this will also be a scalar matrix. Then we add one more condition to this. If in a scalar matrix, all elements along the diagonal are 1, we get what is called a unit matrix or identity matrix. And the identity matrix of order n is denoted by In. So I2, for instance, will be 1 0 0 1. I3 will be 1 0 0 0 1 0 0 0 1. Now for the identity matrix, if from the context the order is clear, then we could also get away by writing capital I for it. There is no need to specifically mention the order if the context is going to take care of that. So these are the various types of matrices that we are going to come across. You all have studied all this in the 12th standard, so I don't wish to spend too much time on this. Let us now go to operations on matrices. Before one defines the sum of two matrices, scalar multiplication or product of two matrices, it's very important to know when two objects are equal. So let's start with equality of two matrices. We say that two matrices A and B are equal if and only if they have the same order and corresponding elements of the two matrices are the same. So two matrices A and B will be said to be equal if they satisfy two conditions. First condition is their two matrices must have the same order, that means same number of rows, same number of columns, and the corresponding elements in the two matrices must be the same. We then write A equal to B. So for two matrices to be equal, first ensure that they have the same order, and then the corresponding elements of the two matrices should be the same. Next, we come to sum of two matrices. Now here, we will be starting with two A plus B is also going to be a matrix of the same order, and to obtain the elements of this matrix, I need to add the corresponding elements of these two matrices. So the sum of two matrices is again a matrix of the same order, and its elements are obtained by adding the corresponding elements of the two matrices. Notice one very important fact over here, that if two matrices have different orders, then they simply cannot be added. Then we come to scalar multiplication of matrices. Suppose I start with the matrix capital A of order m by n, and K is any scalar. Now for our purpose, a scalar will be a real number. So when I say K is a scalar, I mean K is a real number. So suppose A is a matrix of order m by n, K is a scalar, then K times A, this is also going to be a matrix of order m by n, and this matrix will be obtained by multiplying every element of capital A by the scalar K. So K times A is also a matrix of order m by n, and its elements are obtained by multiplying every element of capital A by the real number K. In particular, when K is equal to minus 1, notice that minus 1 times A will be a matrix of the same order, and the elements of A of minus 1 times A will have the opposite sign as the elements of capital A. We will denote this matrix by minus A, and we will call this the negative of A. So this is regarding the sum and the scalar multiplication. These are relatively simple operations. What is not so simple is product of two matrices. Now here again, fortunately you all have done the product of matrices in the 12th standard, so I'll just give you all a brief idea. The first condition is, there is a very stringent condition on the order of two matrices if you wish to multiply them, and that is, suppose A is a matrix of order m by n, B is a matrix of order n by p. That means number of rows of capital A, number of columns of capital A has to be equal to number of rows of B. Only if this condition is satisfied. If the number of columns of capital A is equal to the number of rows of capital B, then and then alone is it possible to multiply these two matrices, and the product will be a matrix of order m by p. So the product is going to be a matrix of order m by p. To get the elements of this product, one has to take the ith row of A and jth column of B. So to get the ijth element of the product, select the ith row of A, jth column of B, so that it will look somewhat like this. See, the ith row of A is going to look like AI1, AI2, AIN. Remember, as I mentioned earlier, the first suffix stands for the row number. So, if I want the ith row of capital A, the elements will be AI1, AI2, AIN. And let's take the jth column of capital B. Jth column of B2J, BNJ. So first take the ith row from capital A, jth column from capital B, and now multiply the corresponding elements of the selected row and the column. That means I'll get AI1, B1J, AI2, B2J, and AIN, BNJ, and then add all such products. So getting the ijth element of the product is quite a complicated business. You have to take the ith row of A, jth column of B, multiply the corresponding elements of the selected row and the selected column, and add all such elements. Notice something very interesting over here. It's quite possible that if I take two matrices A and B, for example, if I take a matrix A of order 2 by 3, B of order 3 by 4, then it is possible to multiply A with B because number of columns of A is equal to the number of rows of B. This is going to be a matrix of order 2 by 4. However, it's not going to be possible to compute B into A. For obvious reasons, number of columns of B is not equal to the number of rows of A. So in some cases, it may be possible to compute AB, but it may not be possible to compute BA. Or the situation could be the other way around, where you can find this product, but you cannot find this product. Another thing that could happen is, suppose I take A to be a matrix of order 2 by 3 and I take B to be a matrix of order 3 by 2. Then I can find A into B. This is going to be a matrix of order 2 by 2 and I can also compute B into A, and this is going to be a matrix of order 3 by 3. So notice that even in those situations where I can compute AB as well as BA, still the chances of the two matrices being equal are very less. One possibility is that the two matrices have different orders and therefore they are not equal. Another reason, as I mentioned earlier, is possibly AB exists but BA does not exist, or the other way around. And finally, even if both products exist, even if both products are of the same order, it would still be too much to expect AB to be the same as BA. So in general, we will say that matrix multiplication is not commutative. That means AB is not equal to BA in general. Of course, there are a few exceptional cases where AB will be the same as BA, but this is not always going to happen. So that's regarding the product. Next, we have the operation of transpose of a matrix. So let's go to the definition of transpose of a matrix. Let's start with the matrix A of order n by n. The transpose of A will be denoted by A raised to T. This will be a matrix of order n by m, and this is obtained by interchanging the rows and columns of A. That means the first row of A becomes the first column of A transpose, the second row of A becomes the second column of A transpose, and so on. So let's look at an example. Suppose A is equal to 1, 2, 3, 4, 5, 6, then its transpose is going to be first row of A is 1, 2, 3. That now becomes the first column. So in A transpose, the first column will be 1, 2, 3 and second column will be 4, 5, 6. Notice that if there are 2 rows in A, there will have to be 2 columns in A transpose, and if there are 3 columns in A, then there will have to be 3 rows in A transpose. So the rows and the columns are now interchanged. That's why if the original matrix is of order m by n, its transpose is going to be of order n by m. Now there are a few properties of the transpose. I'll quickly list them over here, and then we'll go to the definition of symmetric and skew symmetric matrix. Some of these properties are fairly evident. Let's see which ones. And some probably at leisure you could try and prove them. So if I start with any matrix A, whatsoever may be the order, if I take the transpose twice, when I take the transpose the first time, I'll interchange the rows and columns of A. And then again if I take the transpose, I'll be again interchanging the rows and columns, which means I'll be back to square one, the original matrix. So A transpose is always equal to A. So this property seems to be obvious. However, the next one may not be that obvious. Transpose of the sum is equal to sum of the transposes. But you can actually prove this property by taking the elements of A plus B, then the transpose and elements on the right hand side. Remember, to show that two matrices are equal, you will have to prove that their orders are the same and corresponding elements should be the same. Of course, in this property, I am assuming that A and B are matrices of the same order. Otherwise, I won't be in a position to add the two matrices. So here we are saying that if we first add and then take the transpose, or if we first take the transpose and then add, we will end up with the same matrix. So the order of the operation for sum and transpose is not very important. You can either first take the sum and then the transpose, or you can first take the transposes and then add the two matrices. The same thing also works for A minus B transpose. A minus B transpose is A transpose minus B transpose. And if I do scalar times a matrix, and then take the transpose, it's going to give me the same effect as when I first take the transpose and then multiply by the scalar K. The next property is the one that is surprising in a way, because transpose of the product is product of the transposes but in the reverse order. One important reason why it can't be A transpose into B transpose is mainly because of the condition on the orders of the two matrices, which we have to keep in mind while taking the product. So it can never be A transpose into B transpose. So keep in mind that transpose of the product is product of the transposes but in the reverse order. And this result can be extended to any number of matrices. That means if I have product of 3 matrices and then I want to take the transpose, it will be transpose or a product of the transposes but in the reverse order. So it will be C transpose, B transpose and then A transpose. So this can be extended to any number of matrices so long as there are finitely many matrices in the product. Having done these properties, now let's come to the definition of a symmetric and a skew symmetric matrix. matrix. Now the obvious reason why I need to begin with the square matrix is, if A is a matrix of order m by n, remember the transpose. If A is a matrix of order m by n, then the transpose is going to be a matrix of order n by n. So if I expect these two matrices to be equal, the first thing that I need to do is to ensure that they have the same orders, and that can only happen if A is going to be a square matrix. So that's the least one can expect over here. For a matrix to be symmetric, it has to be a square matrix and the transpose has to be the original matrix, whereas for it to be skew symmetric, it must be a square matrix and the transpose has to be negative of the original matrix. Let's look at an example. Suppose I take A to be the matrix A is this matrix, then let me calculate the transpose of A. The first row of A is 4, 5, minus 3. That will go as the first column of A transpose. 4, 5, minus 3. Second row is 5, 0, 2. That is now going to become the second column. Third row is minus 3, 2, minus 8. That will now become the third column. So after interchanging the rows and the columns, I get the transpose to be equal to this. Compare it with the matrix A. You will notice that A transpose is the same as A. So this matrix is a symmetric matrix. On the other hand, if I take B to be B, then B transpose will be, first row is 0, minus 3, 2, that now becomes the first column. Second row is 3, 0, 4, that becomes the second column. Then we have minus 2, minus 4, 0, that becomes my third column. Let me take the minus sign out, so that I get 0, minus 3, plus 2, then plus 3, 0, plus 4, then minus 2, minus 4, 0. Notice that this is minus B. So B transpose is negative of B, and that's why this is an example of a skew symmetric matrix. By the way, there is a very interesting observation to be made over here. What you could do is try giving a few examples of skew symmetric matrices on your own. It is when you are trying to construct such matrices that you will realize that in a skew symmetric matrix, all diagonal elements have to be necessarily zeros. Now the only hint that I am going to give you is that when you take the transpose, the diagonal elements remain where they are. All other elements change their positions, but the diagonal elements remain in exactly the same positions. So that should be enough of a hint for you all to figure out why in a skew symmetric matrix all diagonal elements have to be zeros. This again is an interesting problem. We will show that any square matrix can be expressed as a sum of a symmetric and skew symmetric matrix. It's a it may be neither. No matter which matrix I pick up, I can always break it up into two components, one of which is going to be symmetric and the other is going to be skew symmetric. Now let's see exactly how to go about it. So let me start with any square matrix A. Surely there is no harm if I multiply and divide this by 2. That means I multiply it by 2 and then I multiply it by half. It will be the same as this matrix. Then I break up this 2A as A plus A. Next, I add and subtract A transpose. Adding and subtracting the same matrix is not going to make any difference to this sum. And I am going to regroup this as, let me put A and A transpose together. And then put this and this together. So this is what I get. And now let me separate the two components. This is 1/2 A plus A transpose plus 1/2 A minus A transpose. Let me call this component as B, this component as C. So at least what I have managed to do so far is to write A as a sum of two matrices. B happens to be 1/2 A plus A transpose and C happens to be 1/2 A minus A transpose. Remember, the problem was to show that any square matrix can be written as a sum of two matrices, one of which is symmetric and the other one is skew symmetric. Whenever you wish to show that a matrix is symmetric or skew symmetric for that matter, find out the transpose of the matrix. If at the end you get back the original matrix, it is symmetric. If you get negative of the original matrix, it is skew symmetric. So let's see what happens if we take B transpose. B transpose is going to be transpose of all this. And now recall those properties of the transpose, those four properties that I have listed. Scalar times a matrix and then transpose of that is the same as scalar out into transpose of that matrix. So transpose of scalar times a matrix is scalar out into transpose of that matrix. And now use the second property. Transpose of the sum is sum of the transposes. So it will be transpose of the first matrix plus transpose of the second. And now use the first property for this. A transpose is A. So this is going to be 1/2 A transpose plus A. And that is equal to, matrix addition is commutative. So I can write this as A plus A transpose, which is the same as B. So this component is symmetric. However, if I look at C transpose, I'm going to do a little bit of cheating and I'm going to find C transpose here itself. See, if I do C transpose, this is going to be transpose of all this. Once again, use the property that transpose of scalar times a matrix is scalar out into transpose of that matrix, and that will be transpose of the first matrix minus transpose of the second, which will be A transpose minus A transpose is A, but matrix subtraction is not commutative. Even for numbers, we know that A minus B is not the same as B minus A, but of course it is equal to minus of B minus A. So I am going to use this property, and if I take the minus sign out, I will get plus A minus A transpose. So that is equal to minus C. So for C transpose, I get minus C, That means C is skew symmetric. So that tells us that no matter what matrix we start with, we can always break it up into two components. One is the symmetric part and one is the skew symmetric component. Given a particular matrix, you can always decide whether it is symmetric or skew symmetric by taking its transpose. However, a very interesting question to ask is whether there is any matrix which is both symmetric as well as skew symmetric. One can give several examples of matrices which are symmetric, several examples of matrices which are skew symmetric, and of course plenty of examples which are neither symmetric nor skew symmetric. What we are now looking for is an example of a matrix which is both symmetric as well as skew symmetric. Let me first give you such an example. Suppose I take the zero matrix of order 2. This is the zero matrix of order 2. Let's look at zero transpose. Interchange the rows and the columns. I get back the same matrix. Also, let's look at the negative of this matrix. 0 is the only number which is neither positive nor negative, so minus 0 remains the same as 0. So negative of this matrix is still the same as the zero matrix. So notice that 0 transpose is equal to 0. Also, 0 transpose is the same as minus 0. So this is a matrix which is both symmetric as well as skew symmetric. So if you take this square zero matrix of any order, it will be both symmetric as well as skew symmetric. What is very surprising is that this is the only such example of a matrix which is symmetric also and skew symmetric also. Let's see a quick proof of this. Suppose I take any square matrix. Suppose I take any other square matrix which is symmetric and skew symmetric. So suppose I take a matrix A which is symmetric as well as skew symmetric. Now first of all, because it is symmetric, A transpose should be equal to it. And because it is skew symmetric, A transpose should also be equal to minus A. So if this matrix is symmetric and skew symmetric, both these equations have to be satisfied. Now, the left hand sides are equal, so the right hand sides have got to be equal, so I'll get A equal to minus A. If I bring this to the left, I'll get 2 times A equal to the zero matrix, and 2 surely cannot be 0. That means A has to be the zero matrix. So this tells us that if any matrix is symmetric and skew symmetric, it has to be the zero matrix and nothing else. So the zero matrix is the only matrix which is both symmetric as well as skew symmetric. So that's regarding symmetric and skew symmetric matrices. Before we wind up today's class, we'll also take a look at inverse of a matrix. So let A be a square matrix of order n. Let A be a square matrix of order n if there exists a square matrix B of order n such that A into B or B into A, both products give us the identity matrix, then we say that B is an inverse of A. So, if I can find a square matrix B of the same order for which A into B and B into A, both the products give me the identity matrix of that order, then we will say that B is an inverse of A. Notice that there is this if in the picture. If there is such a matrix, then it will be called an inverse of A. So first of all, there is no guarantee that there will be such a matrix. It only says if you can find such a matrix for which this product and this product is the identity, then we will call that matrix an inverse of A. That's the first aspect of it. Second aspect is, see, I said B is an inverse of A. I have not said B is the inverse of A. But the good news is that if at all there is such a matrix, it's not very difficult to prove that this matrix will have to be unique. So if at all you can find such a matrix, you can be rest assured that there will be only one such matrix. So if B is an inverse of A, no other matrix can be an inverse of A, and that's why, because of the uniqueness, I can give this a name. I can call this the inverse of A, and inverse of A is denoted by A raised to minus 1. So if I go back to this, I'll get A into A inverse or A inverse into A is identity matrix. So if a matrix has an inverse, we will say that it is invertible. A natural question to ask will be, are there matrices which don't have inverses? And the answer is yes. The answer is closely related to what we call the determinant of a matrix. In fact, I think because you all have already studied determinants, I'll be mentioning this again, of course, in the next lecture when we study determinants. If the determinant of a matrix is not 0, then it is invertible. And if it is 0, then it is not invertible. So if the determinant of a matrix is 0, it will not be invertible. That means such a matrix cannot have an inverse. We'll come back to this later. But before we study determinant of a matrix, let's again make a list of some of the properties of the inverse of a matrix. The first property is, if A is invertible, invertible means it has an inverse. So if A is invertible, then its inverse exists and its inverse is also invertible. In fact, inverse of the inverse, just like transpose of the transpose, is the original matrix. Similarly, inverse of the inverse will be equal to A. Then again, if A is invertible and C is a non-zero real number, C is a non-zero scalar, then C times A is also invertible, and the inverse of this matrix will be 1 upon C times A inverse. And the last property is, if A and B are invertible matrices of the same order, this is just so that we can multiply them. So if A and B are invertible matrices of the same order, then their product is also invertible, and we have a nice formula for the inverse of the product. Inverse of the product, again behaves like transpose of the product. It is product of the inverses but in the reverse order. So these are all the various properties of inverses that we will be coming across. In the next class, we will start with determinant of a matrix. That's all for today.